Hello, everyone. We'll probably wait for a bit past 3 o'clock. We have a pretty small class right now, so I'd like to wait for some more people to come on. Say hi to me if you can hear me. And you can ask any questions if you have any, but we haven't talked about much yet. Our TA today will be Brian Liu. So I don't think he's on yet, but we will also be waiting for him as well. Yeah, we're not starting just yet. We're going to wait for a bit more people to come on. I'm not sure how many people attend the other classes during the week, but we only have like about 30 people on right now. We have a lot of things to cover, but I'll probably wait for maybe 3:05. If there are, or maybe 40 people on before then, maybe we'll start earlier. Okay, I'm not seeing too many people coming on right now, so we'll probably just get started now then. One thing to keep in mind is this is just a seminar class, so it's not like something you have to learn for your competitions. It's just a class I hope you can learn some things about math, learn some mathematical topics, and some intuition that maybe you can carry with you into your future when you actually pursue things besides just competitions. So I think that's what this class is more aimed for. And I think a lot of people might also watch the videos afterwards. I don't know if people actually watch the recordings much, but it'll always be up for anyone who wants to watch it. And we'll have a handout as well. So I'll get started now. So today we'll be talking about stochastic modeling, which is another branch of modeling. It's like a category for types of models. So last week in our class, we talked about deterministic models, which were regarded using math to create models that approximated reality and gave us precise answers no matter like how we ran these models. So usually models, we would get some type of mathematical relation. Maybe it's very complicated and we'll need a computer to solve it, but in the end, the answer will always be provided to us from this model. So in a deterministic model, these models would give us a single answer for depending on what parameters we put in. But the difference with stochastic models is that stochastic models produce either random varying results each time or deal with a wide variety of probabilities on what the result could possibly be. So the word stochastic means, let's see. The word stochastic means to be uncertain and regards probabilities, I'd say. So for stochastic models, one example would be what would your average dice roll be? So average dice roll. So we all know from mathematics that numbers 1 through 6 on a 6-sided dice have a 1/6 probability of occurring. So when we average the numbers that are possible, 1 plus 2 all the way to 6, we get, I believe, 3.5. And obviously, you can't actually roll 3.5 on a dice. But if you do the deterministic model, something like this, perhaps you would get that you would roll 3.5. But in stochastic models, maybe what we would do is we would roll maybe 100 dice. So we would roll 100 dice, right? And each time we would record what we would get. So everything's random. Maybe we got a 1 the first time, maybe we get a 5 the second time, and so on until we roll 100 dice rolls. And then these 100 dice rolls, we would take the average of them through all the data, and we'd get something approximately 3.5. So that's how a stochastic model would work. And of course, using random number generators is not the only stochastic method out there, but that's what we'll talk about first. So I'm going to quickly go over some key differences between stochastic and deterministic models. So I'm going to use a D for deterministic versus stochastic. So one thing, deterministic is more regarding usually solving certain equations. So regards solving a lot and using methods to solve these. Versus stochastic, we usually use more, I would say probably more tricks and more computer related ideas, so more computational. And then another thing about deterministic is the deterministic algorithms and methods usually work really well for very large populations. If you recall a lot of the examples we had from the last week, these models, one of our biggest assumptions was that there were a lot of individuals in a certain like group of either animals or different people, things like that. So we had a lot of people in our population. So a big population, because that allows our average rates and everything to be more accurate. Versus a stochastic model, we can have smaller populations, and it won't give us a precise result. Maybe it might give us a variation. Let's say our answers can vary inside this range with a higher chance of being somewhere around these numbers. So it can handle a smaller population well, but then that also means it doesn't give a very precise answer. So no precise answer. While deterministic models are very precise. It'll give you the same answer every time you operate the model. So these are probably the key differences I would say. When you use a model in real life and you need to solve a problem with a model, you need to think about what are your constraints on the problem? What kind of populations are we handling? Are we handling a lot of objects? If so, maybe a deterministic is an easier model to use. But maybe we're handling a smaller number of models, a number of objects inside our model, and there might be a lot of variation in what could possibly happen. So in that case, we want to use a stochastic model. So I'm going to talk about our first stochastic model today. It's called Monte Carlo. So I believe Monte Carlo, I don't know if he's an actual person. He might have been. So essentially, the Monte Carlo method involves taking a problem and say it's regarding probabilities or perhaps chances that certain things are going to happen. And what we do is we repeat a simulation. So repeat simulation. And then this will involve randomness. So there's going to be some random number generator somewhere in this simulation. And then we repeat this a lot of times. So a lot of times. And then we compile all of these results and we give ourselves example like a graph or some type of distribution for what the results look like. So for example, with our dice roll from the very beginning, our dice roll we took 100 different tries. And maybe let's say we had like maybe 16 ones, and maybe we had 13 twos, maybe we had 17 threes, and so on, maybe some number like 26s, a lot of 6s. So in this case, 100 is not a very large number of tries, but in the end, we'll get something that's relatively close to what's actually true. So that's the idea of Monte Carlo. We take some event and we simulate it a lot of times until we get a good result. So there's not too much math relating this. Usually the math will come more in the form of manipulating numbers in the problem, depending on what kind of problem you have. So since we don't have much to talk about Monte Carlo, I'll give you 2 examples on where Monte Carlo could be used. The first one is what we should call an inventory problem. So none of you guys are probably all too young, maybe your parents do, but most of you probably won't have any idea of what running a business is actually like. Running a business, especially when you're doing wholesale or these kind of like retail selling, it's actually a pretty tricky concept because you need to know how many items you want to buy to stock up your shelves. You want to know how much you want to sell things for. You want to understand at what times of the day, what times of the week, do customers come more often so you know when to stock your shelves. So this is even more troublesome for shops that sell very large and expensive items. For example, we're going to talk about fish tanks. So fish tanks shop. So a fish tank, as y'all know, is a pretty big object. Let's imagine like one of those larger, like a small aquarium-sized fish tanks. And if you're a shop that sells these, you won't be able to fit like 100 fish tanks maybe in a small shop. You can only fit a smaller number of them. Furthermore, the more fish tanks you're holding, the more you need to pay to make sure they're all in good condition every day, make sure they're all clean, make sure they're not like cracking anywhere, the temperature's not too hot. So it takes a lot of money to store a lot more fish tanks versus storing just 1 or 2. 1 or 2 is obviously the easier way. However, there are downsides to storing 2 little fish tanks. Let's say you only have 2 fish tanks on your shelves, and then let's say 5 customers come into your shop one day. You sell fish tanks, 2 of them, but the other 3, you can't sell your fish tanks to because you have no more in your shelves. In this case, these 3 customers are going to leave your shop and go somewhere else, and you just lost possible revenue. So how can a shop maximize their profit in this scenario? So there are 2 general options that I just mentioned. We're going to quickly summarize what these options were. So option 1 is to store a lot of fish tanks. So store a lot of tanks. And the problem is this will have high storage costs. It'll cost more money to store all of these. But the benefit is we can sell whenever there are customers. Whenever there are customers. And the second option we can have is we can have a low number of tanks. So store low number of tanks. This will have a very low storage cost. We don't need to operate much. So low storage costs. And then, but then we have the chance of potentially not having these tanks available. So not many tanks available. And this could potentially mean less revenue. So it's not just a problem with how much we're going to store our tanks. We also need to think about how we can order our tanks. Not like order as in purchase and have them delivered. So perhaps if you are storing a lot of tanks, maybe you only need to order once every month. You can order maybe 10 tanks, 20 tanks per month, and maybe you'll be okay. If you have a low number of tanks, maybe you need to order a tank every single week, maybe every couple of days. So you need to plan on how you're going to purchase these tanks as well. Because let's say you are a low number of tanks and a customer comes in and buys a tank. Then maybe you say, oh, okay, we need to order maybe another 2 tanks for next week because we see a lot of customers come into our shop this week. However, next week, no customers come in and you have to hang on to these tanks for the entire week without selling them. This could be very terrible for your business. So there are a lot of things we need to consider. In this case, we'll just consider these 2. So how can we possibly handle this model with these 2 options? So we're going to compare the eventual net profit off of these 2 options. How can we do that? This is pretty hard to just come up with a mathematical equation that'll tell us exactly how much money you will earn after a certain period of time. Because if you have an equation, remember, usually these results are determined. In this case, we can't really have a determined average result because maybe we don't have that many customers, we don't have that many tanks. There's not enough people to say, oh, we can assume an average rate and that would give us an average answer. No, in this case, we want to see the variation. Maybe with option 1, we'll have a good variation, but it'll be on the lower side. Maybe at number 2, there will be higher risk, but higher reward. We want to see these kind of ideas in our model because this will tell business owners key information on what options they should pick. So instead of going a deterministic model, we'll pick stochastic and we'll use Monte Carlo here. So instead, we can make an algorithm. And this algorithm will essentially will take some type of data for how many customers on average come a week, and we'll create a random distribution. So create random distribution of customers. Okay, so essentially maybe we'll make a schedule and we'll say using random number generators, we'll determine that maybe 5 customers come on Monday, 2 come on Tuesday, 1 show up on Wednesday, none on Thursday, and this will all be randomly determined based off some observational data we find from actually observing a store situation. And then we'll create these schedules, and then we'll run our store through a simulation of this schedule. So for example, we'll run the store, and that means that we will simulate using computer code or some kind of computer algorithm. We'll assume there's a store, and we'll feed in each of these customers. If we have a tank and they want to buy it, we'll sell the tank. If there's no tank left, we can't sell anything, we won't earn the money. And we'll also take into account of all the storage costs and operational costs as well. So we'll run the store with the schedule. And remember, this is Monte Carlo, so we need a lot of simulations. So let's say we do thousands of schedules, all randomly generated, and we'll run the store with all of them, and we'll compile the profits in the end. So compile profits, for each option, So in this case, that'll give us a good comparison on potential revenue. Maybe some simulations for option 1 will show high revenue, but at the same time, another schedule pattern that's randomly generated will show low profit. And then we want to compile all the possible values for all the simulations we've done. So here's some computer code. This is not my own diagram. This is taken, I believe, from the University of Washington or Harvard University, one of these two. So in this case, this is a problem that they did for a certain pattern. I can't tell you the exact parameters they used, but in this case, you can see, I believe strategy 1 is the strategy I've outlined versus strategy 2 is the option that I've outlined in the second one. So you can see that by maintaining a large number of tanks in our first option, we see a distribution that looks like this. You know, on average, a store will maybe earn around, I'd say, 800 or maybe a bit below $800 on average. So option 1, average, 800 on average. However, you can see that barely any simulations showed that stores will be earning more than $1,000. So this is, I would say, low variation, meaning that this is like a low risk, moderate reward kind of scenario. So low variation versus option 2. You can say here that a lot of cases actually, not too many, but a decent number of cases actually are below 0, meaning that the store lost money because maybe they weren't able to pay their operating costs with how much money they were making from selling tanks. Maybe they had to pay too much money for all of these utilities. So in this case, they lost money here, but the average money might be like maybe lower than 1,000, but there's a decent number of cases where the store is making more than $1,000. In fact, it like leans upwards almost. So option 2, average, is probably less than 1,000 average. In fact, I'm pretty certain it's less than 1,000, but there's high variation, and this would be an instance of a high risk, high reward scenario. So in this case, what should a shop owner pick? So from my own judgment, I would say if you're a single shop, maybe you're operating the shop with your family, strategy 1, the large number of tanks in your inventory, is probably the better situation. You can guarantee yourself that you're earning money, you'll be able to pay all your costs, and you'll have decent revenue. But if you're a chain store, for example, you have a lot of fish tank stores across America, maybe strategy 2 would be the better option. Some of your stores might lose money, but that's okay because you earn so many stores. Some of your stores will earn a huge amount of profit, and that's what you're looking for. So this all depends on the scenario, depends on the business and the owners. So however, these decisions are up to the business owners to make. And as mathematicians and as modelers, we are just here to provide these two diagrams here, which were produced using Monte Carlo. You can see this is an example of what is called a histogram. We take data and we plot them into these kind of bins. And this will tell us, hey, an example, this is like 450 simulations produced around 800 profit. Versus over here, maybe like 5 simulations produced negative 3,000 profit, which is pretty bad. But that's essentially what Monte Carlo is doing. It's just repeating a certain simulation and trial a lot of times, compiling the data and analyzing the data. That's essentially what we are doing here. So I'm going to go back to epidemics. I think I did promise that we would talk more about epidemics after last week's class. So last week, you might remember, we talked about the SIR model. And this is deterministic. But let's say you live in like a small village in a rural countryside of, let's say, some small country like Italy has some small villages. So we'll say Italy. Italy was hit pretty hard by the epidemic. So this might be relevant. So in this case, with a small population size, maybe a deterministic model is not too accurate. It'll give you the average number, but since we have such a small population, there will be a large variation. So as a policymaker, maybe you want to see what kind of variation can occur with smaller populations. So in this case, if you remember last week, we related our rates. We have our rates of change for susceptible people, for susceptibles, infected people, and recovered people. So I'm not going to go too in-depth on what these mean. If you want to review it, you can go check out last week's seminar. But essentially, we're looking at how susceptible people can be infected and how infected people will recover. And we related the rates of these transitioning from these states, related the rates to how large these populations were in our deterministic model. But for a smaller population, maybe we can't see the rate is definitely that. But instead, we can say a single individual has the probability of let's say, getting infected from being susceptible to infected. So the probability of susceptible to infected, and this probability we would say is proportional to what we determined last week, which would be the size of the population of S times I. So in this case, we're not using derivatives as our rates of change. Instead, we're using probability within a certain time period t. So within a time increment, you'd say, within increment of time t. And in this increment of time, this is the probability that a certain individual might, maybe there's no S here, actually. It might just be dependent only on I. But this is the probability that one individual in S will convert to I. So you would simulate the entire population of this small village. So maybe for like a couple hundred people in the village. And we would see, hey, every single small time period t, maybe you can say this t is like every hour. Every hour, what is the probability that this person becomes infected? And we'll run the simulation for a long period of time, for a lot of simulations, and we'll compile the results in the end. And so I think I did forget to include the diagram, but essentially, if you recall our population, this is time t, our previous deterministic model might have looked like this for the infected curve. So this is curve I. But in this case, maybe your infected curve would look something like this. So it would look kind of jagged because we are doing discrete time intervals. So it would look kind of jagged like this. And it would follow the general trend of the deterministic model, but it would be slightly varying off because it is stochastic. And this can tell us that, maybe our deterministic model will predict maybe this many people will be infected at the worst time possible for our hospitals, right? So at time, this is the peak of the infections. At this peak infection time, the deterministic model might say there will be, say, I0 people infected at one time, and the hospitals will need to be able to handle all I0 people. But the problem is, if a hospital is designed only to handle I0 people, and it's a small population where variations can be large, maybe in one stochastic case, the case would be like this. And in this case, we have way more than I0 people. Let's say this is I1, and I1 is going to be a lot larger than I0, and our hospitals will be completely overwhelmed. So if we're preparing for an epidemic like this, we don't want to just know only the average rate. A stochastic model would be able to tell us how much disease epidemic can possibly variate throughout the period of time, because in reality, nothing is perfectly determined, nothing is perfectly on average. We are looking at probabilities at time instances. So stochastic does a good job of telling us the variation that may occur. And of course, this is maybe a worst case scenario. The best case scenario may be effective curve is something like this. In this case, hospitals are doing even better. We don't need to worry about them. But to account for the possibility that the infectious curve could go this high in the stochastic model, we would want to tell our hospitals, hey, don't just look out for I0 people infected at a certain time peak. Maybe you want to look out for I1 instead. And this will help better prepare our hospitals and our workers and pretty much our entire society to handle an epidemic at its worst. So this is the benefit of using the stochastic model instead of an SIR deterministic approach. But of course, models can go even further than that. So in this case, we've been just talking about the ideas of SI and R. And we've been assuming that the population is just like a general cohesive branch. But in reality, people have communities. People have friends that they talk to. Maybe you're friends with 6 people and not another random 5 people you don't know across the city. So in this case, you wouldn't be interacting with everyone at once. You'd be interacting in terms of like a graph. So example, let's say we have 5 people situated like this. These are 5 people. And let's say we'll number them A, B, C, D, E. And A interacts with C, A interacts with B, A interacts with D, but let's say they're enemies with E, so they don't interact. Person C maybe interacts with A and maybe B only. And then person D interacts with only A, and let's say person E is just by himself. He's like a loner. So in this case, if this were like a small population we were analyzing in like a society for a disease, if person A somehow managed to get the disease, they could transfer the disease only to person C or person D or person B, but not E. So we would not have to analyze person E in this case for person A. And I said specific people in this example, but this could easily be summarized into general communities. Maybe city A or small town A has large connections with small town C. Maybe they do a lot of like different shipping. Maybe they do visits a lot. Maybe people here are generally friendlier to each other versus perhaps town E is very isolated. Maybe it's behind mountains. So in this case, you would perform the SIR, either deterministic or stochastic models between cities that are connected, but not between non-connected cities. So that raises the question of how can we generally produce these kind of networks? Because of course, we're not going to analyze every single city, every single community and see how they're all connected to each other. That's way too much work. So instead, mathematicians use random number generators to create random graphs, which are essentially take a whole bunch of nodes on a graph and use a random generator with a specified probability, so specified probability P, and say P has a chance of node A has a chance of P of being connected with node B. And you'd run this and create a whole bunch of different graphs. And these would be all your different scenarios and your simulations for the population. So in reality, a lot of really good epidemic models all use these kind of generating graphs approach. Random graphs aren't the only graphs. You can generate a whole bunch of different random types of graphs. So graphs would represent a network and the connections between people, communities, and cities. And you would run SIR and the models on these structures of networks instead of just a random cohesive population like we did in our examples. So I'm not going to go into specifics here, but that's essentially how you can improve our epidemic models. And we have maybe 30 minutes, a bit more than 30 minutes left to talk about Markov chains. I think Markov chains are actually a very cool concept. When I first learned them, they were way more interesting than just Monte Carlo. So Monte Carlo is pretty fun to probably use yourself, but not super fun to like always learn about. So we're going to talk about Markov chains. First, we need to understand what a state is. So a state here, as I mentioned previously, is not like the state of Texas, the state of Louisiana. It's like a certain category for what an object can be in, like what properties objects can exhibit. So essentially, let's say we have like the liquid water, for example. Liquid water can be in, just water itself can be in usually 3 states. It can be solid ice, liquid water, or steam. So those are examples of states. So in general, the idea of Markov chains is we're going to analyze how objects can transition between different states. Let's say all of these circles are different states. And we're going to analyze the probabilities of how objects are going to be transitioning from state to state. And essentially, that's how we're going to look at Markov chains. So I'm going to give you an example real quick. So it's a lily pad problem. You've probably seen this in competition math. I believe there was probably an AMC problem that was like this. So essentially what you have is you have a frog. You have a frog on this middle lily pad here. And the frog at every, let's say 1 hour, he has a 1/2 chance of jumping forward and a 1/2 chance of jumping backwards. And essentially, let's say you have this kind of scenario. And over here, you have, this is the last lily pad, and over here is safety. And then over here, on the last lily pad here, we have a snake. And so the snake will eat the frog if the frog goes onto the lily pad. So remember, at every hour, frog has a 1/2 chance of going forward and a 1/2 chance of going backwards. So find the probability that the frog reaches safety, for example. That could be a problem we're looking at. So obviously, due to symmetry, you can see that it's probably half. But we're going to just look at the idea of the scenario here. So example, each of these lily pads can be interpreted as states. So for example, we'll say safety is state one. This lily pad is state 2. The starting lily pad is state 3. The fourth one is 4, and the snake one is 5. So in these states here, the frog from state 3 has a 1/2 chance of going up, 1/2 chance of going down. And if the frog were at stage 2, there would be a 1/2 chance of going backwards versus a 1/2 chance of going forwards. And at safety, you would just stay at safety. So this would be a guaranteed chance of 1 of staying at itself. And then, for example, over here from the bottom lily pad, 1/2 chance of going back and a 1/2 chance of going to the snake. And the snake is also just to itself, you're dead if you go to the snake, pretty much. So in this case, this is an example of when we draw all these arrows for transitioning from state to state. This is called a digraph. And it's a pretty common tool we use when we look at Markov chains because it tells us how a certain object, for example, the frog, can transition from states to states. So for instance, if the frog actually transitioned from state 3 to state 2, after he's at state 2, he would have these probabilities to move to state 1 or state 3 again. So in general, we can actually write some cool probability equations regarding this digraph here. For example, let's say at a certain time t, so at time t, we'll look at the probabilities P1, P2, all the way to P5 of the frog being at that lily pad. So example, let's say it gets a probability of P1 at state 1, P2 at state 2, P5 at state 5. So let's look at first P1. The probability, let's say this is at time t, say probability at time t plus 1. So we're looking at the next step. If the frog takes another step, the probability that he is at P1 of t plus 1 is going to be equal to either, remember, if the frog at the next step is at state 1, the only way he could have gotten there is either he was already in state 1 at time t, or he was in state 2 at time t, and he succeeded with this 1/2 probability here. So essentially, P1 of t plus 1 is equal to P1 of t. The probability is already there, plus half of the probability that he was at state 2, because if he was at state 2, there's a half probability of moving to state 1. So we're going to do that for each of the lily pads. If he's at state 2 at time t plus 1, you've gotten there only if he was at state 3. Because remember, if you're at state 1, you can't go back to state 2. So P2 of t plus 1 is equal to P3 of t times 1/2. And then P3, if you're at P3, at a certain time, the frog, he could have gotten there either from state 2 or state 4 at a half chance each. So P3 is t plus 1 equals 1/2 P2 of t plus 1/2 P4 of t. And then 4 is going to be similar to 2. It's just going to be the half chance that he was at P3. And then P5 is going to be like P1. He can only get there from state 4. So that would just be, or he could already have been at state 5. So P5 of t plus 1/2 P4 of t. So example, this is 5 equations regarding the probabilities at each time step that we've made. And what's cool about a Markov chain is that if we know all the probabilities at time t, for example, P1, P2, P3, P4, and P5, we can use these equations from the transitioning between states to determine all the probabilities at t plus 1. So we're able to move from one time to the next increment of time in the Markov chain by analyzing the probabilities. And this is called transitioning states. So we are basically transitioning from time t to time t plus 1 using these equations. And what's even cooler, we're going to do a bit more complex math. You can probably take a break or something right now if you do not understand matrices. I assure you it's nothing too complicated about matrices, but we're going to use general matrix multiplication here. So essentially, all of these, if we consider P1 and P5 of t as 5 variables, 5 known variables, or let's say unknown actually. And then P1 to P5 of t plus 1, these are also 5 variables. I wouldn't say unknown or unknown because they're all going to be solved eventually. So let's cross that out. So essentially what we're doing here is we are creating, we want to create a matrix like this of P1 of t plus 1 all the way to P5 of t plus 1. And this is our next, this is generation t plus 1. So this is what we're going to transition to. And we can transition to this matrix by multiplying a larger matrix by hopefully the matrix P1 of t all the way to P5 of t. So we can determine the coefficients in this larger matrix by looking at the coefficients on the variables. So example, P1 has a coefficient of 1. So 1. And then P2 is a coefficient of half. And then 0 for the other 3. And then over here, we would have 0, 0, 1/2, 0, 0, 0, 1/2, 0, 1/2, 0, 0, 0, 0, wait, not 0. 1/2, 0, 0, then 0, 0, 0, 1/2, 1. And a very neat thing we need to understand about this matrix right here is that these are just probabilities of transitioning from, let's say, let's number these, 3 and 4. So to transition from, I believe, state 4, to transition from 3 to 4, we look at this third column and the fourth row. So that's a probability of 1/2. That's how we're inserting these numbers into the matrix so fast. And you see a lot of zeros. Zeros are always nice in a matrix. So also, the columns will always add up to 1 because that's how probabilities work. The sum probability of anything is going to be 1. So essentially, this matrix is called our transition matrix. And we'll call this the matrix T. So essentially, if we have, let's say, these matrices are going to be called matrix P at time t. So what's cool is that T times P of time t is equal to P of time t plus 1. And even better, if we know our P0, for example, P0 could be our example problem. The frog is guaranteed to be on lily pad 3. So that'd be like this. It's on lily pad 3. Then we can instantly find any PT by doing PT is equal to T to the power of, I believe, T times P0. So by taking this matrix power, so this is a matrix power, we are able to immediately calculate any value for t. So that's a neat part about a Markov chain. If you're a bit confused about matrices, hopefully this is not distracting you too much from the idea that we're just analyzing probabilities here. The matrix is just a cool way to compute it with a computer very quickly. So talk about matrices already. Let's talk about weather. So bit of a technical difficulty. Let me stop sharing for a moment. And okay. So for weather, meteorology is actually a pretty important topic. So a lot of us undervalue how important weather forecasting is because we either criticize meteorologists a lot. We say, oh, the weather forecast said it's going to be cloudy, but it's actually raining right now. So we criticize them a lot. And usually we don't actually notice we use them too much. But actually, meteorology is actually very, very important because let's say you're planning an event. You need to know what the weather is. Meteorology is the best thing next to a random guess that you're going to get. Because if you just randomly guess what the weather is going to be, that's pretty terrible. You should at least have some kind of a math or physics or science-based guess at what the weather is going to be. So it's better than nothing for sure. And we can use Markov chains to very poorly predict the weather, but it's going to be very much better than just a random guess. So what we're going to do is we're going to find states, of course. We need states always. So let's analyze maybe weather with 3 states. We're going to say weather can either be cloudy, it can be sunny, or it can be rainy. And then these are going to be our 3 states here. And actually, these 3 states, maybe you can say one day, they'll transition from cloudy to sunny, sunny to rainy, rainy to cloudy. And we can find the probabilities for each of these. And we can immediately create a Markov chain to predict weather on a certain day. But that's actually, that's the idea behind using Markov chains to predict weather. We can find like the transitions between all of these states. And we basically just use Markov chains to produce a very not super random guess at what weather is going to be the next day. Maybe you're on rainy right now, you're going to go to cloudy. So you're going to create a 3x3 matrix that t is going to be equal to, and put the probabilities into here. And you're going to get these probabilities by maybe analyzing weather for around a month, maybe a week even. That's going to give a very bad estimate. So let's say I analyze the weather. I don't actually have numbers for weather at my current city, but let's say you actually put numbers in here, and we're able to estimate the probabilities at a time t from where we are right now. So t to the power of t times p0. So we use this matrix to, with a computer to calculate what it's going to be. And let's say we used a graph to graph it. So I've actually done this before, so I know what this is going to look like. So this is going to be our probability, our time t. And maybe right now we know it's guaranteed to be like sunny today. Where I'm at, I believe it actually rained. So let's just say it's sunny anyways. So sunny. And then over here, the other 2 are obviously going to be at 0 probability at time 0 because they did not happen today. But using our Markov chain here, the next day, maybe sunny has, well, sunny this should be 1 actually. Say this is 1. This is a pretty bad graph. Let's say the next day, sunny drops down to like 30%, and maybe cloudy is at 30%, and like rainy is still at 0 or something. So it's going to transition something like this. And in the end, we can get like some variation on these sunny probabilities until in the end, all 3 of these are going to be at like some certain level. And you're going to think like, hey, wait, why is it that after maybe 7 days, I'm getting the same prediction every day? There's going to be like maybe a 70% chance of sunny, a 20% chance of cloudy, and a 10% chance of rainy. Why is it that I'm getting the same probability every single day? And that's due to what it means to be stochastic, right? Remember, we're looking at variation here. Variation on a short time scale in this case is going to be mildly accurate. Maybe on day 2, it's going to still be pretty accurate. Maybe we have like a 30% chance of sunny, and that's what actually happened. That's not too bad. But in the future, the longer we're trying to predict these random events, the more uncertain we are going to be about the results. So when we're looking at maybe a week after where we are right now, we're not going to get any better predictions that are very accurate on what these numbers are going to be. We're going to get very muddied, very general probabilities at, oh, on a certain day, it's going to be this percent rainy, this percent sunny, this percent cloudy. And that's what we're going to have if we just keep repeating this for very large time periods t. So in this case, this weather forecasting method only works for short periods of time. It's not going to give you like 2 weeks ahead. But in general, for a lot of stochastic events, even real meteorology, that's going to be the case. You're not going to see a meteorology report that's going to say, oh, we are pretty sure that in a month, on this exact day in a month, it is going to be cloudy. That's not going to happen because you need a lot of current data to improve the preciseness and accuracy of future predictions. So that's what I wanted to convey with this example. And I also want to say that you'll notice that after a long period of time, these converge to some average number. This essentially reaches an equilibrium, you would say. So numbers don't change after this. And we're going to talk about equilibrium really quickly and different types of states. So these are some complicated words you see in the title here. And I want to introduce this by saying states can be categorized. Let's say we have 3 states, 1, 2, and 3. So let's say state 1 can go to state 2 can go to state 3, and state 3 goes just to itself. And let's say state 2 can go back to state 1. So in this example, state 3 is a pretty special state because let's say you're an object in 1, and at some time you transferred to state 2, and then you transfer to state 3. Now you're stuck at state 3 because state 3 has a probability of 1 of staying in its own state. So if you're in state 3, you're stuck there forever. And this is referred to as an absorbing state because it absorbs everything that comes into the state. And so these can either be beneficial for a model or they can be pretty negative for computing because there are some problems that these causes. For example, if we want to look for an equilibrium kind of result, similar to how we did in the weather, like with the general probabilities, absorbing state will mean that everything is either going to end up in the absorbing state or some other absorbing states. All the other non-absorbing states, so for example, 1 and 2 are non-absorbing states. All of these are going to have an n probability, an equilibrium probability of 0, because no object is going to remain in them forever. They're all going to end up going to the absorbing state, which is 3. So the n probability here, in this scenario, is going to be 1. So in terms of a model, if you're just looking at, hey, what are these going to end up at? If you have an absorbing state, you already know it's going to end up at the absorbing state. Maybe you want to run it and see the exact probability. Maybe you have multiple absorbing states. But in general, you're going to know that it's not going to stay in any non-absorbing state. So, however, let's say that sometimes you don't want an absorbing state. How can we handle this? There's going to be methods I'm going to show you in the future, but quickly let's talk about how we can find these equilibrium probabilities. So if you remember, our transition matrix and our matrix equation looks something like this. This is generally what it looks like, t times p of t. This is transitioning from time t to time t plus 1. And if you have any questions, ask Brian. He's been giving a lot of information out there. You can also ask me, and maybe I'll address it, but try to ask Brian first. And essentially, this is transitioning from state t to state t plus 1 using the matrix t, which is our probabilities. And the cool thing is, if we're, let's say we went a huge amount of time, and now p of t is essentially going to be the same as p of t plus 1. Essentially, it's reached equilibrium, right? Because that means the probabilities at time t and t plus 1 are going to be the same. So that means that we can essentially get the equation p of t is equal to the matrix t times p of t again. And most of you probably aren't familiar with linear algebra at all, but I will briefly tell you what this is. This is a very interesting equation that gives you the definition of an eigenvector and eigenvalue. So these are pretty fancy words in linear algebra. Essentially, any solution of a vector and number, essentially number 1 here, times this is going to give you eigenvalues and eigenvectors for p of t and the matrix t. And you can find all of these very easily with a computer just based off what every transition matrix is. So that'll tell you this method will essentially use linear algebra to tell you what the final solution of the probabilities will end up being. So that's pretty neat because we can use this for some very interesting applications. So I'm going to quickly tell you something really cool. This is a very cool concept you probably never thought about until now, and it's about the Google search engine. So have you ever wondered how Google does it? Like how, when you search something on Google, let's say you search up the word Khan Academy, and Google will pull up a whole bunch of Khan Academy links on the very first page. So basically it's ranking all these online websites by how relevant it is to your search title, and essentially ranking these pages and giving you what's the most popular ones, which ones are most relevant to your question, maybe whatever you're typing in. And that's what Google search engine is doing nowadays. And if you've ever wondered how this works, it's pretty complicated with math, actually. And we're gonna look at the very, very first version of the search engine that Google had. So it's called Google PageRank. You can search it up, PageRank. And it was a very basic algorithm that Google implemented, like the founders of Google implemented for their search engine. And essentially how it works is we're gonna pretend that you're a random internet web surfer. So you're just randomly browsing the internet. And let's say the websites are all gonna be different states. So if you're in a website, like let's say you're on AOPS.com, that would be maybe state 1. State 2 could be Wikipedia. 3 is some other random web page, 4 and 5. We're gonna do like an example of 5 for now. But in reality, it would have been a lot larger. So what's happening is that, let's say this is AOPS and this is Wikipedia. So let's say you're on AOPS, right? And let's say AOPS, somewhere on the website, they have a link to a Wikipedia article. That means that there's a link to Wikipedia. And let's say on AOPS, there's also a link to some random website, website 4, and then that's it. Now, if you're a random web surfer on AOPS, you would have AOPS, I see some people say. So if you were on AOPS and you were randomly browsing around, eventually you would click a link and leave AOPS is the assumption you're making. So if you were to randomly click one of these 2 links, there'd be maybe a half chance you go to Wikipedia and a half chance you go to state 4, which is some other website. And for Wikipedia, let's say Wikipedia is very, very knowledgeable. You have links to all these websites. So links to 5, links to 4, links to 3. And in this case, since there are 4 options you have, each of these will be probability 1/4. Because if you're on Wikipedia indefinitely, you'd eventually reach some link and you'd click it and you'd go to one of these 4 websites. And let's say website 3 only goes to website 4, so that's a probability of 1. Website 4, let's say, since we also have to realize I made a mistake here in my calculations with 3. 3 can't only go to 4. Actually, 3 can't only go to 4. My bad. So 3, let's say, only has a link to 4. It's probably of 1. 4, let's say, has a link to, let's say, 3. And that's a probability of 1. And then let's say 5 has no links to any website. It only stays at itself. So that's a probability of 1. So now, based off this digraph, so we can take this digraph of websites, and we convert this, based on the probabilities you see here, into a transition matrix T. And I have a lot of states here. This is a 5 by 5 matrix, and I'm probably not going to fill it all out for the sake of time, but you'd have this transition matrix here. And ideally, if you were to see, let's say, the random web surfer, which web pages they're on the most often, because that's how you're going to rate these pages, right? If there are more people on a certain website regarding whatever you're searching for, you would want to display that website first because it's more popular. So you can determine the probability of a single web surfer being on a certain website using the transition matrix and the eigenvalue technique I just talked about. So to do that, we need to make sure we have no absorbing states. Why is that? Because an absorbing state would cause the final probability that you get, like the P infinity, to have zeros and then finite probabilities only on the absorbing states. Because if you're a web surfer, eventually, let's say you're in this case, you'd eventually turn up at state 5 and you'd stay there forever because there are no links to any other websites, and that sucks. But then Google did something very, very clever here. They said, hey, a web server is not just to stay on state 5 forever. He's going to eventually exit website 5 and then maybe find some other random website to go to, like a random website. So what Google does is he removes the probability of 1 that 5 stays on itself and says instead of this happening, 5 has a random 1/5 chance of going to any of these other 5 states, including itself. So instead of the probability of 1 being, instead of the last row here looking like 0, 0, 0, 0, 1, Instead, what it's going to look like is it's going to look like 1/5, 1/5, 1/5, 1/5, and I'm probably missing 1/5. So it's going to look like this instead. And that's going to remove the absorbing state we have. So essentially what we're doing is we're removing the absorbing state. And by removing the absorbing state on 5, boom, there's no more absorbing states. We can use the methods we talked about earlier and instantly calculate the probabilities that web surfers are on certain pages. So maybe say Wikipedia is the most popular for this one search is the most popular, followed by maybe highest probability on AOPS, and then some other websites. And then Google would look at this and say, okay, let's list Wikipedia first, then AOPS, then the other websites. And that's how Google would use to page rank all of these different websites. So that's a pretty neat trick using Markov chains. Let's see, I have examples here. We're not going to explain these with actual matrices. We're just going to tell you how this relates to Markov chains. Essentially, Mendelian genetics. You probably learned this in biology a bit. This is called a Punnett square. Punnett square. And essentially, it's relating alleles between parents and children. So that's pretty neat because you can say, define states of certain alleles. An allele, two parents with, like, let's say in this case, YY, or something like that, maybe has a certain probability of producing two children with another set of alleles. And you can use this to create a Markov chain, find your transition matrix, and then evaluate the probabilities and the ratios of the population being in certain alleles and phenotypes and genotypes. So that's how you can use Markov chains with genetics. That's pretty neat. Another cool thing, anything with these cycles are very neat because this is an example of the nitrogen cycle. And I have a cow here. Cow eats grass. Grass is nitrogen inside, so its poop now has a lot of nitrogen. And this gets decomposed into the ground, follows all these processes, and nitrogen essentially moves around everywhere in an ecosystem like this. So you can classify this into a whole bunch of states. Let's say this is cow, this one is like decomposers, and then you use this, and you use like a fraction to represent the portion of nitrogen. And you're assuming, let's say nitrogen molecule is moving through the ecosystem. What is the probability at a certain point in time that it is inside the cow? It's inside decomposers, it is inside all of these different processes. So you can use that to analyze how well maybe nitrogen cycle is performing in a certain ecosystem. Another example, this is a project I actually did myself. This is called Mercury Bioaccumulation. Essentially, it is the theory that mercury in the ecosystem, bioaccumulation, it assumes that mercury is accumulating in an ecosystem because animals generally have no process through excretion to remove mercury from their bodies. So it ends up that big, long-living fish will end up eating a lot of smaller fish with a lot of mercury inside, and it'll accumulate more and more mercury with each trophic level in an ecosystem. And this will cause a lot of mercury in big fish like this. So you should not eat these a lot because humans are harmed by excessive mercury. You can get mercury poisoning. So you should be eating these sparingly, like larger fish. That's the idea. So we can analyze each of these fish or like essential parts of the ecosystem, including the water, and we can analyze how much mercury at a certain point in time is in these things. And we analyze from a very long point of like period of time, see if it's going to be safe in the future, what we can do to reduce these effects and things like that. And the last one, Monopoly. You've probably all played Monopoly before. It's a very interesting board game regarding spending money, financing, investments, these kind of things. And just a bit of luck as well, because you need to roll dice. And that's where we get the idea of, hey, let's use this stochastic model here. So with Markov chains, each of these tiles becomes a Markov chain, like a state in the Markov chain. So what's the probability of you being in a certain point at a certain point in time, like a certain area? So let's say you all have a probability of 1 of being on go. But then after, like, let's say T rolls of dice, what is the probability of where everyone is at? So interestingly enough, there are no absorbing states in Monopoly because you can always move from one square to another square in a certain period of time. So with Monopoly here, we have no absorbing states. So hey, if we analyze the probabilities of transitioning for every single state, which is pretty complicated, but it's possible, we can get a huge transition matrix. It's going to be very big. But then the best part is we can use the eigenvalue method to find the probabilities at any point in time eventually. So using this method, you can find out which properties are the most landed on, so you know which properties are more valuable, which ones are worse. And I don't remember the exact results. If you're interested, I believe these orange properties are always very, very valuable to go on because people land on these a lot. And I can't remember anything else, but this was always pretty good profit if you're interested. And so that's essentially how we can apply Markov chains to monopoly. Let's see. I have maybe, I can probably talk for another 5 minutes. You're free to go now if you want, but let's talk about diffusion very, very briefly. I've definitely not enough time to completely talk about diffusion, but what essentially diffusion is it is the random spreading and dispersing of, so random dispersing of objects with time. So it is not the same as bulk flow, not bulk flow. Bulk flow is essentially like wind, or like you're blowing. You're essentially moving all the air in front of you by pushing on it. That's what bulk flow is. It's not bulk flow. It's a random dispersion of objects. So I had a cool GIF I wanted to show. Let me try to pull it up right now. So you can see here that this is an example. This is a GIF of air diffusing in a small rectangle. So you can see it starts off, let's look right now, it starts off on this halfway mark, and the air is slowly dispersing its molecules randomly across the other side. This is not, air spreading like this is not the cause of bulk, it's not the cause of bulk flow. It is because it is diffusing across this boundary. And that's essentially what diffusion is. I'm gonna go back to my screen. Yeah, so how is diffusion related to stochastic models? Well, that's because we're handling a lot of random movement here. A certain molecule at a certain point in time has a certain probability of being in a certain area. And that's what we're looking at with diffusion. So I'm going to talk about the random walk. You've probably all heard of the random walk in probability. You start from a certain point in 0, and you have like a certain probability of moving to the left and to the right. So it's kind of like the lily pad problem. You can use Markov chains to evaluate this. But essentially, you can keep moving infinitely to each side. So negative infinity and positive infinity. And the question is, what does the distribution look like at a certain time? Turns out that after a very long time, your distribution looks like this. You have like this probability of being at some point x at a certain point in time. And this is actually a bell curve. And the name of the distribution is a normal distribution. And you can prove that this is a normal distribution using a theorem in statistics called the central limit theorem. We're not going to talk about that because we're going to talk about, I'd like to talk about fixed law real quick. So essentially, let me get this to work. Essentially, a fixed law is just a law using density and a bit of calculus, and it essentially says that you have this differential equation right here. This is a very complicated equation, but what we're going to take out of it, this is a very elementary approximation. We're going to say, hey, this is 1 over t, so 1 over time is going to be proportional to some number d, it's called diffusivity constant, times 1 over distance squared. So this is a cool law just to know about. And it's pretty relevant. I'm going to talk about some examples. I'd like to talk about how modeling is used rather than the exact math. So diffusion, why does diffusion matter? So for smokestacks, when we construct smokestacks, we want to calculate a factory if it's emitting toxic chemicals from the smoke. We want the chemicals to diffuse and spread out enough so the density is low, and people down here, if you're a person down here, you want to be able to breathe in the smoke from the smokestack at a low density to where you're not harmed by it. That's why smokestacks are constructed so high. So by using diffusion modeling, we can compute how much will diffuse after a certain amount of time while it's falling, and we can determine how safe it is to build a smokestack at a certain height h. So by increasing height, we increase the cost, but at the same time, we don't want it to be too low or else people will be harmed. Another example, this is an example, this is a theory called the Turing Theory. It's just one of many theories as to why animal spots look like this. And essentially, the Turing Theory says that there are chemicals in an animal's skin that diffuse as they're growing, as they're forming, and they will react to each other, but because of the diffusion, it'll create different zones of reaction. So you can see that some people did a project here on how diffusion is working for these things. You see these are patterns produced via certain interactions. That's one example of how we can use stochastic models of diffusion to approach these different kind of questions. Another one is a very famous diagram. This is an example approximation of human migration. So how humans started off in Africa and traveled all the way to the Americas in a certain period of time. How did this happen? We can use diffusion models to examine how humans followed these animals, how they just randomly spread, and how they traveled eventually to the American continents. So those are all examples I have today. I'll end the class now. Thank you for staying, to all of you who stayed for this extra 5 minutes. If you have any questions, feel free to ask me right now or on Discord. I'm going to release the handout hopefully by the end of the weekend. And thank you for attending. Yeah, and so if you enjoyed these topics, you can always search up more information about them, read the handout, learn more, but at the same time, focus on what you need to do. If you're interested in this, feel free to learn about it. I'm not going to force you or anyone to, or pressure you guys to learn about these topics, but I think it's interesting. And I hope you find it interesting as well. So thank you for coming to today's lecture. Can I go back to the time distance constant equation? Okay. The diffusion equation, fixed law, you said? I'll assume you meant this. If you want me to prove it, okay. So this is a lot of calculus actually to proving this equation if you're interested, but I'll give you the brief outline of what kind of ideas we need to prove it. So essentially what we're going to examine is we're going to examine like a passageway like this. So we're going to use this rho here. This is the Greek letter rho. This is density. So we have a lot of density distribution. Let's say we have density distribution here, but no density here. Maybe a different density here, like P2. And we're going to see how these are interacting in different regions. We're going to like block these off in different areas of distance x. And you're going to analyze how flowing is occurring between these boundaries we've designed. So by analyzing how these materials flow, you use flow rates like density times like velocity, for example. Velocity is actually equal to the derivative of position with time. So by analyzing these kind of rates, you can get several integral and differential equations that will relate density versus time versus position using flow rates. So I'd say that's the most important concept. So flow rates across boundaries. And by solving these integral equations, you can essentially get to the conclusion. You don't need to solve them. You convert them all into partial differential equations, and you can eventually get this law right here. That's how, at least how I was taught this law. So yeah, I hope that was a sufficient enough proof. If you're actually familiar with calculus, there are a lot of proofs of fixed law online. You can easily search it up yourself. But another interesting thing is the fixed law is actually related to the random walk. So if you were to look at the probabilities in the random walk, like the probability of being at position x at time t, this probability, you can actually relate these to differential equations as well. So if you do that and you actually manipulate these, you can actually get a very, very similar equation to fixed law. So these like complement each other, they're the same meaning, and essentially how we can verify that, oh, random walk is the same as analyzing density flow rates. So that's what I would have talked about if we had more time. Not the exact details like you asked for, but essentially how these random walk and fixed law are related. And heating is an example of diffusion as well if you're interested. So that's about it. I'm probably gonna end the class now. If anyone has any more questions, please ask in the next like 30 seconds or so. And thank you for coming, everyone. It really means a lot for me to teach these things that I enjoy so much to other young students. Yeah, so thank you for coming, everyone. I'm going to end the class now.